My name is Wooi Lun.
And my name is Bryan, and today we are going to analyze the XRD pattern of a crystal.
With the sample being NI3SI2. We start our analyzing process by plotting a NI3SI2 XRD diagram based on the data provided. And this plot was compared with the database in the Material Project website. After comparing the data, we obtained 3 peaks which align closely with the database. These 3 peaks correspond to 3 planes in the NI3SI2 crystal with their own parameters shown in the diagram. We can determine the lattice parameters using two equations, Bragg's law and interplanar spacing. Using Bragg's law, the d-spacing of 3 peaks obtained before are calculated, which matches the data provided in the Material Project.
From Materials Project, we know that NI3SI2 is orthorhombic, which has the following interplanar spacing. Plugging in the planes gives a system of 3 equations. Solving the system of equations gives us the lattice parameter A, B, and C, which matches closely with the values provided in Materials Project. Now that we have determined the lattice parameters, we can move on to the crystal structure itself. From Materials Project, we know that Ni3Si2 is a base-centered orthorhombic structure, also known as a C-centered orthorhombic. The figure on the right is the conventional unit cell, and while this may look complicated, we can actually break this down into a BCO structure with a 10-atom basis. This means that if we want to know the structure factor of Ni3Si2 as a whole, we can break it down by analyzing the structure factor of a BCO and the structure factor of the basis separately. In fact, the structure factor of a BCO directly tells us what planes are allowed and what planes are forbidden, while the structure factor of the basis merely modulates the intensities of the different peaks. For a BCO, identical atoms occur at the origin and at half-half zero. This leads to the following diffraction conditions. When H plus K is even, constructive interference occurs. When H plus K is odd, destructive interference occurs. Taking the 3 planes chosen from before, we can verify and conclude that for Ni3Si2, constructive interference occurs when H plus K is even.
Now, let us consider the chemical bonding of Ni3Si2. Firstly, we take the electronegativity difference between 2 atoms to know the type of bond between the atoms. According to the calculation, we know that the Ni3Si2 fall between the polar covalent bond region. Now, the question arises, does the Ni3Si2 only consist of covalent bond? Do all the valence electrons involved in the contribution of covalent bond? Assuming this is the case, and we take the oxidation state of silicon as -4, in order to fulfill the 3:2 ratio, this means that nickel must donate 2.67 electrons per bond, which doesn't really make sense. This explains why the crystal have 10 atom bases, because one unit cell consists of different sizes of inequivalent atoms bonded in different ways, but not just the same type of bond repeated symmetrically. So, Ni3Si2 is just the formula unit of unit cell consists of 48 Ni atoms and 32 Si atoms, and the oxidation number are just merely the average of charge distributed over the whole crystal. Therefore, we can infer that not all the valence electrons involved in the formation of covalent bond only.
Since we know that not all the valence electrons of nickel and silicon are involved in covalent bonding, we are now required to look at the electronic configurations in order to determine the behavior of the electrons. Nickel is a transition element, and hence 3d electrons with partially filled d orbitals are involved, leading to 4s electrons coming into the picture later. And as for silicon, the valence shell consists of 3s and 3p orbitals, with the 3s orbital being more tightly bound to the nucleus. In order to determine the types of bonds that can exist, we need to know the ways in which the orbitals can overlap. And we indeed find that there exists a nickel-silicon covalent bond which is polar due to the overlap between the 3d orbital from nickel and the 3p orbital from silicon. The rest of the orbital overlaps lead to metallic bonding, with the primary contributor being the overlap between 4s orbitals between adjacent nickel atoms. In terms of the band gap, we see that nickel dominates. We don't just see the valence bands near the Fermi level being filled, which is due to the covalent bond between nickel and silicon anyways. We also see the bands across the Fermi level being partially filled, due to the nickel 4s state and also the 3d 4s hybrid state. This means that the nickel 4s orbital is highly delocalized with a wide bandwidth, which leads to a band gap of 0 electron volts. This overlapping band gap means that Ni3SI2 has a metallic character. So, Ni3SI2 has both a covalent character where the electrons are localized, directional, which characterizes the geometry of the crystal structure, but also a metallic character where the electrons are delocalized, non-directional, leading to good electrical and thermal conductivity and other such physical properties. Therefore, we can now say that Ni3Si2 is an intermetallic compound with hybrid covalent metallic bonding between nickel and silicon atoms, supported by metallic bonding between adjacent nickel atoms.